Right, so here we go with CCEA, A2 Physics, Unit 2, Fields, Capacitors and Particle Physics for June of 2018. Let's get started. Question 7. Figure 7.1 shows the basic structure of a synchrotron. A synchrotron is an accelerator used to progressively increase the speed of particles as they travel in a circular path of fixed radius. A1. Describe how the circular path of fixed radius is achieved. So you need to explain that the magnets here are providing a center-directed force on these charged particles. As they move around, they are pushed towards the center. But if the charged particles got faster, they would come out further because the radius is proportional to the momentum. So you need to increase the strength of this magnetism to compensate. So force is provided towards the center by the magnets, and by making them stronger as they accelerate, you can keep the particles in a fixed radius. Part 2. In this synchrotron, the magnetic field is maintained using superconducting electromagnets. Explain why superconductors are used to create the magnetic field and how superconducting state is achieved. So you're trying to produce very strong magnetic fields under very tight control. You need to be able to produce very high currents to make that happen, and so we need superconductors. So to achieve a strong controllable magnetic field requires very high currents, and hence superconductors are used. And then you just explain that you're using a cryogenic liquid to get them down below their transition temperature. Part 3. The acceleration cavities are connected to a high-frequency alternating voltage. The frequency of this voltage is increased as the speed of the particles increases. Why is this necessary? So you're explaining there that it must stay in synchronization with the accelerating particles, otherwise they won't keep accelerating. Part 4. The particles can be accelerated until their speed approaches the speed of light. Explain how the particles can continue to gain kinetic energy but no longer increase their speed. So remember that when you approach the speed of light, 0.99, 0.999, 0.9999, each increase is only like a tenth of the previous increase. And so there's very little change in speed at these values, just a tiny increase in the last decimal place each time. But what we do see at these speeds is Einstein's equation coming into play, the E equals mc squared, and what happens is that the particles gain mass and their energy goes into large increases in their mass, and so they gain kinetic energy by the m in half mv squared increasing. Part B. Protons are accelerated through the accelerator complex at CERN in various stages before being transferred to the synchrotron known as the Large Hadron Collider, with an initial energy of 0.45 tera-electron-volts. The LHC has 8 cavities, each with a potential difference of 2 megavolts, which accelerate the protons. How many orbits of the LHC must a proton complete to reach a final energy of 7 tera-electron-volts? So they're coming in with 0.45 TeV. They've got 8 cavities, and each one of them gives a push of 2 megavolts, which will give them 2 mega electron volts. You can imagine a singly charged proton that's got the charge of an electron. Then if you put it through 2 megavolts, then from W equals QV you get 2 mega electron volts per push, and there's 8 pushes per loop. So each push on a proton across 2 megavolts is going to be 2 mega electron volts. And if there's 8 pushes per orbit, then that's going to be 8 times the 2 mega, which is going to be 16 MeV. So we just need to know how much increase we need. So the total increase is the energy they end up with, 7 tera electron volts, minus the energy they come in with, which is 0.45 tera electron volts. So that's our total amount, 6.55 TeV, and we've got 16 MeV per loop. It's just going to be the total energy divided by the energy they get per loop, and that gives you approximately 4.1 times 10 to the 5 orbits. And that's that. Thanks for watching.